All right, so these are the first parts off the printer. They gave us a lot of valuable information. So I'll walk through each of those. So before I talk about these parts, let me just kind of tell you about the actual printing process first, and then I'll get in more details behind the actual parts. So when you look at the overall print time for this job, from preheat to cooling for these parts, it was about 10 hours. And that was for a printed depth of about 33 millimeters. So there's definitely an opportunity to improve this as I continue. And I'm going to talk through kind of each phase. So in the preheat phase, I have the 110 volt version. So my preheat time is set to 70 minutes. That's by default. That's based on what Pavel and Thomas have experimented with to get optimal results, and probably some safe, kind of maybe a conservative factor in there as well. Because it appears that my system, based on the thermistors and the thermal camera, and you can see on this picture, this is at about 52 minutes, and you can see that all the temps here are pretty much where they need to be at in 52 minutes. And then I took another picture at 66 minutes, and basically it's the same temps. So by default, you can see mine's sitting, a lot, maybe longer in this preheat phase, longer than it needs to be. So it could very well be that 60 minutes is the right number for me. But that will be with further experimentation. But if you have the 230 volt version, I believe they say the preheat time is less than 45 minutes. All right, so the bed prep phase. So after preheat, the printer gets prepared. It lays down about another 13 millimeters of powder on the print bed, and this prints or lays down a layer at 0.1 millimeter intervals at a time. And at this point, the surface temp increases a little higher than the preheat stage. I believe it goes up to about 172. Now this step for me took about 90 minutes. And the reason why you put this bottom layer is it's really similar like the top cap. It acts as a thermal barrier between the parts to help prevent warpage during cooling. So depending on how virgin your powder is, there is some expansion during this step in that bed prep phase. So when it heats up, you may see like what we call tearing of the surface. In my earlier videos, you saw it really kind of, the powder expands and it rakes off a piece. And then over time, it tends to repair themselves. And usually this print job, I saw it had some tears about, at the 3 millimeter layer mark. And then before I got the 4, it actually had repaired itself. What we did find though is we found that we lowered for the next print, we lowered the surface bed prep temperature down a couple degrees, and and I discovered that actually solved. I had no tearing actually. So now when auto tune is enabled, and I highly recommend you keep auto tune on, then around at the 4 millimeter layer during this bed prep phase, what you see is the auto tune kicks on and it starts heating the surface slowly, the surface area a couple degrees, a few at a time, and it actually it's looking at the surface. And what happens is directly under the halogen lamps, you start to see discoloring. Now for me, that happened around 187. It starts to turn dark. So this is the system detecting the melting point of the current powder you have. So if you've mixed different ratios and so forth, you may have a slightly higher temperature where this occurs. But anyway, when it hit the 187, then that point auto tune says, okay, we detected it at 187, and the algorithm then resets. And then at that point, it lowers the print surface temperature for me about 10 degrees. So at 177, then from then on, it maintained the temperature at 177 for the remainder of the 0.1 millimeter layers to get to the 13 mils. So this temperature is probably, it's obviously the calculated temperature they have in their algorithm that says basically it determines what the surface needs to be in order to be sintered properly when the laser scans it. Okay, so it continues at 13 millimeters well, and so this took a long time, longer than I thought it should, and I believe this was really impacted by the parameters I'll discuss. It happened the same thing in the printing phase. But basically after each layer it coats, it wants to make sure that layer gets up to the temperature of 177. Well, that happens literally like within 5-10 seconds of putting down that layer. So right now the algorithm in mine, it took a lot longer than that. And I think we reduce that time, then we'll improve overall time. I think we can improve it by half. You could probably reduce the number of bed prep layers, less than the 13 millimeters, but then you run the risk of your parts warping, and frankly, you don't need that. So, all right, the print phase. This step took almost 5.5 hours. That's for 33 millimeter layer of print height. And if you do the calculation, that equates to about a print speed of 6 millimeters an hour. And of course, this unit's spec'd at 9 millimeters an hour at a 25% scan and density. Now, my density was around 32%, so that would explain maybe a small part of that because it's longer laser time. But my problem wasn't the laser time. My problem was actually the time heating between the layers. So if you look at the process, it takes the recoater about 6 seconds to put down a new layer. And then, like I said, it took 13 to 30 seconds between layers before the laser started. This is where we need to improve. And we basically found out, we discovered some things here. But bottom line is, when I was looking at my camera, it scanned that layer on, it said 177, and it stayed at 177. So really that resonant time only needs to be about 4 or 5 seconds at max. When we went back and looked at some things, my thermal camera, the pixels in my thermal camera they measure a little bit higher, maybe some hot spots we'll call them. And Pavel says they actually think that was impacting it because their parameters is they want to make sure that there's stability across the temperature range before the laser starts. And I think with those hot spots, it may have been influencing the system and it was waiting longer. And so Pavel went ahead and made some changes in the config file and kind of eliminated those outliers in his thing. And for the next print, we saw a significant improvement. So I think we're good there. So in fact, I was seeing about 5 seconds of heat time when the layer went down before the laser started on this next print job. So a layer heating time of 5 seconds at this print and packing density, I would have seen maybe closer to about an 8.4 millimeter hour or overall less than 4 hours for this print job. We're seeing some sort of laser light leakage. We're not really sure exactly maybe where that's coming from, but that's something we'll have to continue to look at. All right, the cap layer goes on. It's a 1.5 millimeter layer, and right after it finishes the print job, it starts that. It took about 20 minutes. And of course, with the new algorithms, it should go faster now. And this layers obviously helps with the warpage piece. Now the cool down, it's the minimum for any project is 2 hours, is the way they have it set. And they have a cooling factor built in the profile that can be adjusted, but I think it's like 30% of the time to print. And so that would say this should take about 2 hours and 10 minutes to cool down. It actually takes a little bit longer than what it says. So that's just something that they'll have to look for in the future to see where that discrepancy is. Okay, let's get to the parts. All right, so first impression, I thought the parts, looked really, really good. I mean, they're fairly smooth for SLS parts, to be honest with you. And they were very detailed. You can see in here, that I've got some engraved numbers there. The SLS4ALL, this snapped, I'll talk about that later, but the numbers and letters look really good. Overall, some parts, when you really kind of look at it, magnification, they showed some scanning lines. Thomas said that would indicate that maybe the laser spot dimension might need to be adjusted. However, the overall parts, these parts felt really light, and lighter than I would expect it, because I actually purchased other SLS parts outsourced, and particularly these parts here, and they seemed a lot less, and they were. I weighed them, so I knew density was an issue here. Well, I'm going to explain what I did for density measurements and dimension measurements. And part of the reason, I mean, the fact that this snaps so easy, you can see in here, it's a very porous kind of crystalline structure. That would make sense that it was, you know, probably not at the right density. And so I'll talk about how, what we discovered there in terms of why. One other note, I did print this part, it has threaded printed threads, and I thought it was pretty impressive. I mean, right in there, I mean, it threads right in. Now, I did break this part because I threaded it in, you know, about, I don't know, about 5 millimeters. And then I pulled on it. It took a lot of strength. I was trying to break it to failure, and it took a lot to pull that out. And when they're more dense and stronger, I think I probably won't even be able to do that at all. So, all right, let's talk about the density. So I use these 3 sets of parts. This is called a fill plate. This is called a nut plate. And I had these in different orientations as well. So I had a couple like this, and then you can see I had 2 in one direction, 1 in the other. And so that was able to look and see differences in X and Y difference as well. So basically, when you look at these, I used these to get an average of the density. And when you look at sintered PA nylon, it has a density, PA12 nylon, it has a density of 0.95 grams per cubic centimeter. And when I measured and weighed these and took the volume, I got 0.75 grams per cubic centimeter. So that did not surprise me. And as I discussed with Thomas, he thought the energy density during the printing may have appeared to be low, and the particles were not sintering completely. And he said there's a setting to improve the fill energy density, but actually another discovery helped explain the reason the laser energy was diffused. And so I think after fixing that problem, and I know for a fact after the new print job, it fixed the density. So that was the problem. And so, I mean, let me just be honest with you. The problem was the galvo window. So the instructions say to clean the galvo window and the glass window before each print. So I've done about 5 print attempts without actually the laser coming on, because I kept failing during the bed prep phase. And so this was actually the first print job the laser was actually activated. So I really didn't even think looking at the galvo window. Well, needless to say, I feel a little foolish, because when I removed the window, it was covered in a film, as you can see here. So we all agreed that this was probably alone was a primary root cause for the laser being diffused and had less energy density, and was the reason for the lower density parts. So obviously that galvo window shouldn't be, it was more of a film, and they said it shouldn't get like that. And they thought my main glass window maybe was not fully tight against the machine there. And after checking, several of the screws needed about a quarter turn to fully tighten. So that could have been the problem. All right, let's talk about dimensions. You know, there's 2 main factors that impact dimensions: scaling and shrinkage. Now, scaling, if you look at your print bed, scaling is going to be more of the, you know, obviously dimensions nearest the laser should be the best, and we've already done the scaling pattern to make sure that as it got out to the outer perimeters that the scaling was corrected. And so if you print these in different portions of the bed and you see different X and Y movement differences in different portions of the bed, it means you probably have more of a scaling. For most of it, it's probably going to be more of a shrinkage. They already have built-in factors. They have 3% shrinkage built in the X and Y direction, and I believe 2% for the Z direction. And so on average, my parts, these parts here, they measured about 0.6 larger in the Y direction and about 0.4% in the X direction. And the Z actually was pretty much spot on. So, but because of the density issue and everything else, I really, you know, I figured that's probably not the dimensions as far as the shrinkage factors probably, I'm not going to change anything, and then on the next print, then if everything looks right, which they did, I'll use those as my shrinkage factors. That's pretty much the parts and the analysis on this parts. And so some of the things I want to tell you. Clean your galvo window and main protector window after each print attempt. I mean, you're not going to get the optimum laser energy to get to the right density and the strength of the parts. One of the things too, as we go through the analysis, we really got the point, we reduced the bed prep temp to 172. This eliminated all the tearing for my next print job. And then obviously Pavel updated the algorithm on the thermal camera to detect those outliers and adjust for them in the calculation. So this improved the print speed per hour. So let's talk about then the new print. So these are just, I printed several different parts. You can tell the difference between these and these. They're heavier, they're glassier almost. They look really good out of this next print job. And the density was 0.96 grams per cubic centimeter, so pretty much spot on where we need to be. And now, in dimensions here, I'm actually now that these centered at correctly, I need to make some shrinkage adjustments. Probably, basically they were X and Y. They're approximately about a 0.7 and almost 1% off in the X and Y. And so I made those adjustments in my file. So for the next print job, my parts probably should be more spot on. In other words, they had calculated 3% shrinkage, and mine parts were actually only seeing about 2% shrinkage. So that's about the difference here. So pretty happy. We finally got the system. We're getting it dialed in. And that takes, basically for your system, you're going to have to do something similar. But overall, man, this looks really, really good.